let us start this lecture with a thought process from Jim Eden from Sheffield University. He says that you are a big chemical reaction. Everything you say, all that you do, all that you see, decide or remember, think or feel is nothing but the manifestation of the chemical reaction, that is you. It is a very profound statement, and I told you nature does a lot of activities through us with the help of chemistry. That is the beauty of this, and let us recall briefly what we had learned in the last lecture. We basically discussed about Hayes law, and then we moved to how to find out adiabatic temperature. Then the adiabatic temperature, we found out that it is function of equivalence ratio, it is a function of inlet temperature, it is a function of also the pressure. And keep in mind that what I had derived in the class, last class, that is mean for constant pressure process. However, some of the process occurs in the constant volume process. You need to think how we will have to find out adiabatic temperature for that. And remember that I did those things keeping that this chemical composition being known, but however, in real situation chemical composition is not being known and both are interlinked. And then we moved into equilibrium, because from at equilibrium we can find out, we learned that by minimization of the Gibbs free energy, we can find out the equilibrium composition, right. And keep again, I must draw your attention that this minimization of Gibbs free energy can be applied only for the control volume process at what we call or the constant pressure process, right. And if I want to go for a constant volume heat addition, like in a combustion bomb or a for use for calorie use as a calorimeter or for a IC engine, then I need to use the Helmholtz free energy, Helmholtz free energy. That means, we need to minimize that. You will have to look at it. I won't be covering, I will be concentrating on the minimization of Gibbs free energy. Let us look at how we will be dealing with it, and as I tell you, we will have to basically look at the procedure for determining the equilibrium compositions. And I have just identified few steps. Of course, first of all, one has to look at what reaction it is. When you talk about reaction, you will have to identify probable equilibrium species. You may ask a question, how I will know that? Of course, you need to have some experience, and even if you choose something just by guessing, then you can figure it out at the end of this calculation whether it is of worth doing that or not, because the composition, if it is very very less as compared to the measure component, you can say I can neglect it, but you will have to pay a price for that, because number of equations will be increasing. Then you need to what you call identify the equilibrium reaction scheme, that is also is the important aspect. What are they, and then these reactions must be elementary in nature, that is a very important point. Then you need to find out equilibrium constant. What is that equilibrium constant? Some of you might be aware, because it is being taught in the your engineering and other things. So, we need to determine that equilibrium constant, right. And then of course, for that we will have to next step would be strike a balance for elementary conservation, strike overall mass conservation, and then minimization of Gibbs free energy, right, and solve all equation by iterative method, because all are coupled equations. So, you cannot really solve like that, although it is algebraic, but it will be coupled. So, you need to use the iterative method. One of the numerical tool which is being used is the Newton-Raphson method for solving. So, we will, as I told, we will be considering ideal gas mixture all the time. So, Gibbs function for IS species can be written as the GIT. That means, this is the ith species gives free energy at particular temperature, and this is at standard state, like temperature and pressure, and then plus RUT ln Pi by P naught. You keep in mind that Pi is basically partial pressure of the ith species, and T is the temperature, Ru is the universal gas constant, right. That means, this expression is meant for a particular species. It can be methane, it can be propane, it can be oxygen, it can be OH, any other things. So, what it indicates, it depends on temperature, it depends on also partial pressure, and P naught is your what you call the standard pressure, in this case ambient pressure, which is being considered. So, Gibbs function for an ideal gas mixture, we know that G mixture will be summation of Ni G I R and Ni into G I T R U. You can just write down this expression over here, if you look at this expression can be put it over here, that is all, or rather this expression can be put it here and you will get this thing. So, what we will do now? We will have to basically find out d G, capital G of mixture is 0, right, at equilibrium, because at equilibrium this will be 0. So, then what I will do? I will just differentiate this expression and d n I, keeping this as a constant, this I will be keeping as a constant. So, I will get d n I G I in the bracket naught plus R U T ln P I by P naught. Okay. And similarly, n I will keep it constant, I will be differentiating this what you call Gibbs function, because this is Gibbs function, right, and I am differentiating it. What I will get? If I differentiate d G I T, what will happen? It will be constant. So, therefore, that this term will be 0, right. Similarly, because if I look at basically it will be d G I T 0 is 0, because it is not changing with respect to, it is with respect to what, I mean like whatever the temperature, standard temperature kind of things, it will be having, or sorry, it will be at with a certain temperature. So, it will not be really changing. So, that will be 0, and we will find that this d ln P I by P is basically d P I by P. If I take a summation of that partial pressure, it is equal to when you take our partial summation of all partial pressure over the all of each individual species, then what you will get? You will get the total pressure. So, that will also be won't be changing, right. So, if I take a summation of that, summation, because since the pressure remains constant in this, you can have a 0. So, therefore, this term will be 0. So, what you will get, the d G mixture is nothing but d n I into this Gibbs function for a ith species. So, this is a very important expression you should keep in mind, which is being used for finding out composition. Keep in mind that these values from where I will get? I will get from Janov table. And in my book Fundamental Combustion, it is given on the back side these data, and of course, partial pressure, and this is the total pressure from which we will be getting basically the mole fraction, that I will see in the next slide, or we will discuss about it. So, let us consider a arbitrary reaction, that A moles of species A is reacting with B moles of species B, and it is going to the C moles of species C and D moles of species D. It can be any numbers, but I have considered only 2 reactants and 2 product, just for simplicity. And what are these A, B, C? If you look at A, B, C and D are corresponding stoichiometric coefficients, that means how many moles it is participating, that is saying. And change in number of moles of each species, for example, species A will be proportional to the coefficient of that species A. In that case, d n A is equal to minus K A. K is what? K is your proportionality constant. And why it is minus? Because the reactant is getting consumed, therefore, it is minus. Similarly, d n b is equal to minus K b, and whereas the d n c is equal to K c. Keep in mind, this is positive because it is being produced. Similarly, d n d is equal to K d, and K is the basically proportionality constant, right. What we will do now? We will substitute this above relation it gives function what we have derived. At equilibrium, this d g mixture will be equal to 0, and we will be substituting here all those expression and sum it over. For example, if I take for A, A and B, it will be minus A, and keep in mind that there is a K here, because A K, this portion I am taking from here and putting it here, and G A naught T plus R U T ln P A by P naught, because the species is A. Similarly, minus there will be K here, and G B T naught plus R U T ln P V by P naught, just you write. And then similarly, I can write down for species C and species D, is that clear, which is equal to 0, right, because this is nothing but what? This is basically G mixture, right. D G mixture is equal to 0 at equilibrium, you keep in mind, and we will be knowing the temperature also, we will be knowing the pressure, right. So, and then if I will do what I will do now, I will basically rearrange these equations. What I will do? I will put this G C T kind of corresponding to the standard state like C and D for, and then this thing, if you look at this portion is basically delta G naught, that is corresponding to the what you call standard state and temperature, and these you can get from Janov table, right. That means delta G naught is known to you, and then minus R U T ln is equal to P c by P naught and P d by P naught divided by P a by P naught P v by, and this we call it as basically this term, this bracket term we call it as a K p. What is this K p? K p is the equilibrium constant, right, and this equilibrium constant, I can write down K p is basically E power to the minus delta G naught R U T, right, into this portion, that is K p. That means, this is known, if you look at this portion is nothing but that, and then this is known, am I right. Similarly, I must be knowing the temperature at which I am finding out the equilibrium. That means, in the real situation it will be adiabatic temperature, So, T will be known, and of course, the R u is known. So, you know this term, that means, you know basically K p value, okay. And then you will have to find out this basically P naught is known to you or not, P naught is known, but do you know P d, P c, P a, P b? You really do not know that, right. You do not know those things, right. Can we express this partial pressure of spaces like P c, P d and then P a, P b in terms of mole fractions, right. Let us the power to the C plus d minus a minus b. But if this pressure is what? This is the pressure at which you are trying to find out equilibrium composition. If this happens to be atmospheric pressure or standard pressure, this term will be P by P naught will be 1. Okay. That means, this term will be basically 1, you need not to worry about, but however, sometimes we will be looking at a higher pressure or a lower pressure than P naught. So, this for the generality I have kept, but in some book you may find it is not there. Okay. So, now take I will take an example and illustrate how we can determine this not equilibrium compositions, and also I will tell you the steps how you can find out both equilibrium composition and adiabatic temperature, right, that I will have to show. And then of course, this you cannot do in in your day to day life or in your as a part of curriculum. So, we will be taking a simple example which can be done in classroom. Okay. So, let us look at 3 moles of hydrogen are reacted with 1 mole of oxygen at ambient temperature and pressure, right. We need to determine the equilibrium product. So, what is given? Given is that initial mixture ratio is given. That means, 3 moles of hydrogen is reacting with 1 mole of oxygen. I know that, and pressure is given, temperature is given. So, what I will have to do? I will have to first assume the certain reaction. For example, I can write down 3 moles of hydrogen, 3s2 plus is reacting with 1 moles of oxygen, that means O2. What are the product I can think of? Can I guess? It will be definitely water, will be oxygen, will be definitely will be there, right, may be there, may not be there, right, and O will be there, OH will be there, right, and several other things, but we will consider few of them like hydrogen, oxygen, water, H, O and OH, and several other spaces one can think of. Keep in mind that more spaces I take, more it will be number of equations I need to consider. So, that means these I have guessed, this spaces is being guess. So, then I need to identify the possible elementary reactions. Keep in mind, we need to always consider elementary reaction, and that is hydrogen can be converted into 2H. When I talk about it, I can determine what is Kp. So, Kp by definition it will be Ps square divided by Ps square. If I talk in terms of mole fraction, it will be Ys square P naught divided by YH2. Why it is? Because 1 P naught is cancel it out. Are you getting my point? Because in this case the P naught is being cancel it out in the denominator, right. So, similarly, this is our equation 1, and I will take oxygen is going to 2O, O2 is going to 2O. Then similarly, I can get a relationship for equilibrium constant, that is Kp2 PO2 divided by PO2, right. PO is equal to basically YO2 square mole fraction in P naught divided by YO2, right. Similarly, I will be considering H plus O going to the OH, right, and I can write down Kp3 will be POH divided by PO and pH. You keep in mind that these are all mole fraction, YOH divided by YO, YH, and P naught comes in the denominator, right. And then I will have to look at S2 plus O, S2O, and Kp4 PS2O divided by PS2 PO, and you will get the in terms of mole fraction. That means, I am getting these 4 equations. If you look at, we need to find out 1, 2, 3, 4, 5, 6, right, but we are only considering the 4 equations here, or we are getting 4 equations because as you are considering 4 elementary reactions, right. Keep in mind that I may not take this combination, but I may take some other combination as well. Then we need to actually maybe it will be clear little later on that why we need 4, why not 6. Okay. As I told you previously in the procedure, we need to talk about elemental balance, right, and those things are important as well, otherwise you will be in deep trouble, right. So, we will be getting 2 equations from that. Let us see what we will get. Let us say that 3s2O is reacting with oxygen going to A of water, B moles of hydrogen, C moles of oxygen, D moles of H, E moles of OH. Just for the simplicity I have written. So, if you look at number of H is equal to what? 6 given, yes or no? 3s2, that means 6, and number of O atom is basically 2. So, if I take this H, what I can write down? 2NS2, because 2 are there in S2. So, similarly, in the water 2NH2O plus H, it is only one. So, NH plus NOH is equal to NH, that is the product what I should get. If I look at the product balance, all the things I am talking about in the product wherever it is there. If you look at hydrogen, water, H, OH. Similarly, I will be looking at oxygen. If you look at 2NO2, NS2O is there, NO, NOH and N. That means, these numbers reactant and the product should match. So, what I will do, I will just divide this by the total number of elements whatever is there. So, if I divide this equation for H, right, I will get 2YH plus 2Y water and plus YH plus YOH is NH by N total. And similarly, when I divide this by N total, right, total. So, I will get 2YO2 plus YOS2O plus YO plus YOH NO divided by. Now, what I will do? I will just divide equation A by B, right. What I will get? This will be when I divide this thing, that N total cancel it out. I get 2YS2 plus 2Y water plus YH plus YOH divided by 2YO2 plus YS2O plus YOH. So, this is known. If you look at, this is known. What is that? That is basically 6 divided by 2, right, which is given. So, this is one expression, equation number 5, and another we need to get another equation to find out 5 unknowns, 6 unknown basically. So, that is yi is equal to YH, YH, YOH, YS2O, O plus O2, right. These are the spaces, and then I will get 1, and we can look at this 6 solve these equations, and such that we can get these values. So, what I will tell you, that means, let us look at how we can go about this. We know that P is given, T initial temperature is given, what is that, and initial mixture ratio is given, right. So, initial temperature must be given, because that is the point, and then what you will do? You will have to assume value of adiabatic temperature, right. And after assuming those adiabatic temperature, then you will have to compute this equilibrium compositions, right, P and T, by using this minimization of Gibbs free energy, right, and then estimate that heat of reaction what I am getting, right. So, if you look at whatever this thing I have told, like in the previously, like you need to solve 6 equations to get those compositions, because Kp and other things will be known. So, you will get composition. Then you will have to estimate heat of reactions, because you have assumed adiabatic, you do not know really adiabatic, then estimate the new adiabatic temperature from this heat of reaction, which we had done already by invoking the first law of thermodynamics, right. And by knowing this, you will have to find out, you have guessed this value, you have obtained this value, then what is the error you are getting. For example, I will just assume 2000 Kelvin, then I am getting 2001 or 2100 Kelvin. So, naturally there is a error, which I cannot tolerate, for example. But if you can say, look, it is only 5% error, I need not worry about it, then you can manage. If it is less than error, then if it is T adiabatic is equal to T adiabatic star or the gas value, then you can stop, right. If we are happy with the error whatever it is coming, let us say 1%, 2%, 3% you can tolerate, then you can stop. But suppose you are not happy, like if T adiabatic star is greater than the error, tolerable error, then you will have to find out the what will be the new gas value. That means, this T adiabatic plus alpha minus T adiabatic minus T star kind of things. So, right. So, what you will have to do? So, you will have to basically use a relaxation parameter, generally people use under relaxation parameter, alpha is less than 1 kind of things. And because if you give a over relaxation, sometimes you may get instability problems. So, then if you are not happy with this, then you will have to guess value, this is a new guess value, you will have to go to the step 1, and then that is the way it will go on iterating, and you will do and then estimate those values, right. So, now let us look at an example which we will be dealing in the classroom kind of thing. If CO2 gas is heated to 3000 Kelvin at a constant pressure of 0.2 megapascal, we need to determine percentage of CO2 that can be dissociated into CO and O2 during this process. So, if you look at the temperature is given and the pressure is given, right. Here it is temperature is known, unlike the previous case where you do not know the temperature, right. Therefore, you need to go and do it to find out percent of carbon dioxide. So, carbon dioxide is basically reacting going to the CO plus half O2, right. And if you look at the what are the coefficients for this case, CO2 is 1, CO is also 1, but oxygen is half. These are the stoichiometric coefficients. So, assuming ideal gas behavior for all component, equilibrium constant can be expressed as Kp y CO CO nu CO, that is coefficient, and YO2 its corresponding coefficient divided by YCO2 corresponding coefficient, as a stoichiometric coefficient of carbon dioxide, P by P naught, and these are the coefficients, right. And what we will have to do, we will let us assume that x moles of CO2 dissociated into CO. Then what will be the reaction? That will be CO2 will be half 1 minus x CO2, and we are assuming that YCO, and there will be some oxygen ZO2, right, because the reaction can proceed this way and there can be go that way, right. So, therefore, we need to find out, we are assuming that this will be the product, the CO2, CO and O2. Again, this is an kind of assumption one has to make. So, we will have to do a C valence. If I look at this is the left hand side is 1 is equal to 1 minus x plus y, right, because there is in the Z there is no oxygen here, there is no carbon here. So, y is equal to x. So, O balance we can get 2, that is for the O, 2 into 1 minus x plus y to z. So, z is basically x by 2, right. So, total number of moles will be basically 1 plus x by 2, because this will cancel it out, right, 1 plus x by 2. So, if I look at that in a tabular form, is a constituent gases CO2, CO and O2, and these are initial moles, these are equilibrium moles what we are assuming, because x is not known, we need to find out x basically. Then mole fraction you can say 1 minus x divided by this total, and similarly for carbon monoxide x divided by 1 plus x by 2, and for oxygen x divided by 2 into 1 minus 1 plus x by 2, right. So, what we will do now, we will substitute these values, these values over in the Kp, that is equilibrium constant, and we must be knowing the equilibrium constant from knowing the change in Gibbs free energy at a standard state. So, what we will do, we will basically Kp is equal to E minus delta G by T by RUT. So, we know the temperature. So, we will substitute this value 3000 Kelvin, this and these values from the Janov table. If you look at this, I can take from Janov table, right, and then I know these values, right, from Janov, because delta G T I know, if you express that will be G, like all those things, and then you will get those from the table. So, these values will be known, but whereas Kp is YCO and all those things we know, and we will substitute this in place of this mole fraction from the table of these values, right, I will get, and then this is known. So, we need to solve, because if you look at this expression is basically, if you look at this expression is basically in terms of x only, right. So, if I will get this x, then I can get what will be the equilibrium composition for the species being considered like CO, CO2 and oxygen. So, what I will do, if you simplify this, you will get this 4.948 and then this, and then you will have to simplify further, and you will get a basically a expression which is cubic in nature. Sometimes very rarely, of course, you will get a quadratic equation. If it is quadratic, you can get easily. Of course, some of the calculator you are having, you can solve cubic equations, otherwise you will have to do a iterative method. And keep in mind that here the pressure comes into picture 0.2 and this is 0.1, that in this example it is very important, this term you cannot really neglect. So, iteratively if you solve this equation, you get x is equal to 0.8643, that means the percentage of carbon dioxide that dissociate into CO is basically 86.43%, and you can get other composition as well. It is a major one in this temperature. If temperature is low, what will happen? Naturally, this percentage will be much lower values, right. If you consider the ambient temperature, it is really won't be, nothing will be happening, kind of things, right. So, now this we have discussed about chemical equilibrium compositions, right, and now we will move into basically kinetics. So, if you look at this is basically a specialized branch of physical chemistry dealing with study of chemical reactions and their governing factors. So, when you talk about this chemical reaction, it can be homogeneous reaction, it can be heterogeneous reaction. So, when you talk about homogeneous reaction, I have taken an example, 2CO gas plus reacting with oxygen going to the 2 moles of carbon dioxide. Keep in mind that all are in gaseous phase, but in what you call in propulsive devices, we may need to deal with heterogeneous reaction, particularly when you are looking at solid propellant combustion, right. So, that means where one of these reactant or even product soot and other things happen in combustion is the carbon CS is in solid form, it is reacting with carbon dioxide is a gaseous and going into the 2CO. So, this is basically based on the physical state, whether it is a gaseous phase, all the reaction, all the components of the participating species in a reaction, or one of them is the what you call different physical state like solid or a liquid, right, then we call it as a heterogeneous reaction. But if all is in the same phase, we call it as a homogeneous reaction. So, chemical reaction can be divided in 2 categories based on the fastness of reaction. One is explosive, which is quite very fast as compared to the non-explosive reaction, and is a slow, we call it a deflagration, whereas explosive reaction we call it a detonation kind of thing. We will be discussing little later on. And then chemical reaction depends on, if you look at on the species concentration, temperature and pressure, right. We have seen already from the equilibrium point of view, but the reaction rate when you talk about it will be we will see little later on that it will depend on that. So, if you look at reaction rate, it is basically rate of decrease of reactant concentration or rate of increase of product of concentration. Generally, it is expressed in terms of mole per meter cube second, but in some cases we will be looking at kg per meter cube second, how much mass it is being consumed per unit volume kind of things. So, if I look at a compact expression of chemical reactions, which you can look at like V I dash M I going to the product of V I double dash M I. Keep in mind that this is a summation which is of various species, I can be 1 to n. Similarly, on the reactant side, I is equal to 1 to n, the number, and V I dash double dash are stoichiometric coefficients of reactants and product. Of course, M is the arbitrary specification for all chemical species we are considering, but I will take an example and show you what is it. It looks to be little quite complex, but in it is quite simple, and it is being used when you are basically using a coding kind of thing. Suppose you are doing a modeling, it is very useful, but in our case it may not be that useful. But when you want to model the chemical reaction using basically numerical tools, this is a very, very handy way of expressing chemical reactions. So, let us take an example that if I take 3H plus hydrogen going to the hydrogen and H H, then in this case what is the N? N is the number of species. What is that N? N is equal to basically 2, because one is hydrogen, other is H. So, and similarly if I take H plus O2 going to the HO2, in this case N is equal to 3, right, because one is oxygen, other is hydrogen, other is HO2. Keep in mind that this reaction what I am considering is elementary in nature. So, if I want to write down this in a compact form, what it would be? M1 is H, M2 is S2, right. If I look at this is my this thing, I is equal to 1 to N I dash M I, I double dash M I, right, I is equal to 1 to N. So, if I look at what is this Vi1, in this case it is what you call 3, because H is there. What about V2 dash? V2 dash will be 0, because there is no S2 over here. If I look at M2 is S2, in the left hand side is not there. So, therefore, this will be 0, right. And similarly, if you look at in the right hand side, that is H, if you look at it is V1 dash is equal to 1, whereas in the what you call for the hydrogen in the right hand side V2 dash is equal to 1, because hydrogen is there. And similarly, I will you can think of about this is a similar way, like in the left hand side if I consider the hydrogen V1 dash is equal to 1, for the product what will be V1 double dash is equal to 0. Similarly, oxygen there is a mistake actually. So, this will be 1, right, and V2 dash will be 0, and M3 is basically HO2 and V3 is equal to 0. There is nothing on the left hand side, right hand side is equal to 1. So, the above reactions are elementary as I have told you. So, global reactions will be like 2 moles of hydrogen reacting with oxygen going to the product of 2 moles of water. And if you look at what is really happening, this is one hydrogen and another hydrogen and oxygen, they will come and collide with each other. So, that the bonds are broken, and if you look at there is a one bond which is having formed, that is a water. That means, how many bonds? This is 1, 2, 3, 3 bonds are being broken, 4 bonds are being formed, like kind of thing. So, it is quite this is I mean if you look at this is a quite difficult things to happen, right. So, the 3 bonds are to be broken and 4 bonds are to be formed, because which is unlikely to occur, right. So, therefore, it is global reactions is very unlikely to occur. I think it will be clear when I will be talking about this what you call collision theory. So, similarly, we can see that in 1 mole of methane reacting with 2 moles of oxygen going to the carbon dioxide and water. If you look at this is 1, 2, 3, 4, 4 bonds are there, and similarly, oxygen 1, 2, like 6 and 1, 2, 3, 4, 5, 6. So, if you look at this is a quite a difficult to happen in real situation, because too many bonds are to be broken, too many forms, and this should come together, so that it will be having effect. So, therefore, global reaction is really won't be possible in real situations. If you note that just now I have invoked the concept of breaking of bond and the forming of bond, explaining a global reaction for both methane and air and hydrogen air. But this is just to explain you the thing. You must keep in mind that
such kind of breaking of bond and forming of new bonds are not really being taking place in the global kinetics. In other words, these breaking of bond or the forming of new bonds are likely to occur in the elementary reaction only. Just to explain, I have invoked this concept, but you must keep in mind that this is wrong to say that this process of breaking a bond and forming of bonds are occurring for global reactions. So, but whereas what is likely to occur is the bimolecular and trimolecular reactions may occur. So, let us consider reaction between two molecules, that is A, moles of species A reacting with B moles of species B going to the product C moles of species C and D moles of species D. So, I can write down this reaction rate is basically 1 over A dC A by dt, right, and this is the minus sign because it is getting consumed, and similarly equal to the dC V by dt 1 over B minus sign, because B reactant is getting consumed, is equal to 1 over C dC by dt and 1 over D dC by dt. So, if you look at what is saying, it is saying that reaction rate for each species, one case it is getting consumed, other case is getting produced. For example, if I take H plus reacting with O is going to the OH, and I can write down in similar way like dC H by what you call by D, I can write down this is dC H by dt minus is equal to dC O by dt minus is equal to dC O H by dt. Keep in mind that this reaction rate, when you talk about in this example dC H by dt is proportional to what? Concentration of hydrogen and oxygen. When you talk about this concentration of hydrogen and oxygen, then it has to be constant. So, that constant we call it as a basically rate of reaction kind of thing. So, if I sum it up this discussion, then we need to invoke the law of mass action, because how this I could write. Then the law of mass action states that the rate of reaction of a chemical species is proportional to the product of concentration of participating chemical species, where each concentration is raised to the power equal to the corresponding stoichiometric coefficient of chemical reaction. So, this is a very important statement, right, which governs the reaction rate and other thing. So, for example, if I say that in a very compact form, reaction rate of IS species will be proportional to the product of all the species which will be participating on the you can consider as a reactant side and corresponding to their stoichiometric coefficient. So, I can write down this is a proportional. So, therefore, K RRI is equal to K summation of CMI VI, and K, as I told, it is a specific reaction rate or the rate coefficient, right. So, these we need to determine, right. How to determine that is a very important aspect. So, K depends on the temperature and it will be dependent on activation energy. Of course, it does not depend on the concentration, because the is already according to mass law of mass action, that it is basically a proportionality constant, already concentration are there. Keep in mind that this law of mass action holds good only for the elementary reaction, it cannot be hold good for the global reaction what we will be using, that is a very important statement you must keep in mind. So, question arises how to determine the value of K, right, that is a very important aspect. So, we need to look at collision theory, right. What is the collision theory? Collision theory is basis the molecules will be moving randomly and it will be colliding with each other, and when there is a colliding with each other, it will be having collide in a proper orientation. That is the first important thing, and then it should have enough energy to do what? To break the bond. So, that is basically one has to look at it. As I told you, what happens during chemical reaction? I must repeat that it is basically existing bonds are broken and new bonds are formed, and that is the way of life, like new old things goes out and new things come in, then only life will be there, otherwise no, right. So, similarly for that you need to have enough energy, right, because the molecules are colliding with each other in a random motion. So, therefore, whenever there is a problem, it will be something new things would come out of it when there is a collision, and it should have enough energy kind of things. So, but what is the condition of dissociation of bonds, because the bond is broken. If it is a broken, then it must have enough energy, and when you talk about this enough energy, and also this has to molecule has to be collided in a proper orientation, right, then it should go to a very higher level, and then of course, it comes as this is what you call as I told, colliding molecule must have possess higher energy than the mean energy level, otherwise it will not really make any impact. So, what will happen during this reaction? So, what will happen, this is having a reactant, it will be colliding, it will go to the activated complex kind of a higher energy level, and then it will be drop out and it will get to the product. Keep in mind that this diagram I have shown here is meant for a exothermic reaction, because if you look at the product is energy level is lower than the reactant, and this difference of course, what we call is the heat of reaction. So, what is the probability of this collision being taken place, rather a successful collision being taken place, that will be depend on the Boltzmann energy distribution, which states that probability of a molecule possessing a threshold energy E, what do we call it as the activation energy, is proportional to exponential E by RUT, right. So, condition for chemical reaction to occur, what I have already told, I want to repeat that suitable molecule must collide with each other, and the molecule must collide with proper orientation, that is determined by a steric factor, and colliding molecule must possess enough energy greater than the threshold value, that we call it as a activation energy, right. So, from the collision theory we can find out that our reaction rate is basically ZAB, S is the steric factor, and probability is basically E power to the minus capital E RUT, and this is capital E is basically activation energy, and this is of course Boltzmann energy probability factor and steric factor, and collision frequency. What is the frequency with which collision will be taking place? So, from kinetic theory of gases, one can get ZAB is basically Ca Cv sigma AB square. Keep in mind that in the collision kinetic theory of gases, you consider as a sphere, right, and this sigma A is basically average diameter which will be going, and this diameter will be diameter of the each molecules, right. And if you remember that 8 pi kb, kb is basically Boltzmann constant, right, and T divided by mu, mu is the reduced mass, that is M A, M B divided by M A and V B. This is the collision theory, I am not getting into detail, maybe you can refer some books to get that, and this is the square root of that velocity. So, and if you look at the reaction rate comes as C A C B, and sigma square A B is basically 8 pi k b by T by mu. S, I mean if I club all those things, because I will put it over here and I will get these values. So, and if I club all those things, these values together, right, and keeping this temperature out, this portion of this I can write down as B T power to the 0.5 C A C B E power to the E by R U T. So, then K, if I look at K is basically B T power to the 0.5 E, minus E by R u t. So, if you look at A is basically is known as pre-exponential factor and which is basically A is equal to B power to t. So, this you can put it as a your law of mass action or reaction rate you can get. So, if you look at if I plot this ln k with respect to the 1 over t, I will get a slope values, right, and which is from this if I conduct experiments find out this k and other thing, I can get what is the like activation energy from this slope, and getting these values whenever it will be 0 like when the temperature is very very high and it will go, you will get a value here, that is your pre-exponential factor, you can get that one. So, the form of equation previous section we can write down like is known as Arrhenius law, right, but there is a limitation of this Arrhenius, it cannot simulate the combustion process over a wide range of temperature, that is the limitation, and rate law matches experimental data at high temperature. Of course, it may not match at the low temperature. For example, this portion it may not match, but however, it is matching in this portion because this is this curve corresponding to low temperature. So, therefore, one has to take care of that, and keep in mind that variation reaction with temperature is quite really interesting, because if I go on increasing, you will see this reaction rate goes up, of course, it goes down because the species will not be there to be reacted. And keep in mind that this is goes by exponential. So, therefore, an increase in temperature by 10% for the same activation energy can cause the reaction rate to be enhanced by 250%, right. So, this is a very important aspect, and one has to worry about this kinetics part, and I will stop over here, and then we will see in the next lecture about the other aspect of this multi-step chemistry, and then look at it. Okay.